Light moves through the universe at a speed so great that, on everyday scales, it can feel almost instantaneous. For a long time, scientists treated that speed as simply one property of light itself. But gradually, a deeper picture emerged. This was not only about light, it was about the structure of spacetime, and about the way cause and effect remain ordered throughout the universe. Once we begin to look at it that way, the speed of light feels less like a curious number, and more like one of the quiet rules that keeps reality coherent. This is not just a rule of physics. It is a rule that holds reality together, and understanding it takes us to one of the deepest connections ever discovered. A bridge between quantum mechanics and the structure of spacetime itself. So take a moment, slow down, and let your mind follow this idea. Because once you truly see what this limit means, you may never look at the universe the same way again. Galileo Galilei climbed a hillside outside Florence in the year 1638. Carrying a lantern and an almost impossible ambition, he set out to measure the speed of light. His assistant waited on a distant hill with an identical lantern. Instructions memorized and timing carefully rehearsed. The experiment seemed elegant in its simplicity. Galileo would uncover his lantern. The moment his assistant saw the flash across the valley, he would uncover his own lantern in return. Galileo would then measure the delay between sending the light outward and receiving the returning signal. Divide the round-trip distance by the elapsed time, and the speed of light should reveal itself. Galileo's idea was elegant, and for its time, remarkably thoughtful. Yet each attempt led to the same impression: the returning light seemed to arrive without delay. That did not necessarily mean light was instantaneous. More likely, it meant the delay was simply far too small for human reaction and the instruments of the 17th century to detect. In that sense, Galileo had not failed. He had run into the limits of scale. Light travels through empty space at approximately 299,792 kilometers per second. At this velocity, light crosses a 1-meter gap in about 3.3 nanoseconds. Human reaction time, by comparison, is around 250 milliseconds, which is about 250,000 microseconds. Galileo was effectively trying to measure a delay of only a few nanoseconds using instruments and human perception that could barely resolve a quarter of a second. The signal was completely buried in noise long before it could ever be detected. To measure the speed of light, scientists would need distances large enough for those tiny delays to accumulate into something measurable. Earth was simply too small. The solution would eventually come from the heavens. From an astronomer carefully tracking the motion of moons orbiting a distant planet. Not a delay measured over miles, but one that accumulated across hundreds of millions of kilometers. Ole Rømer arrived at the Paris Observatory in the year 1672 as a young Danish astronomer eager to make his mark. His assigned task seemed routine. He was to track the orbital motions of Jupiter's moons, particularly Io, the innermost of the 4 large Galilean satellites. Astronomers used Io's eclipses behind Jupiter as a kind of cosmic clock, carefully timing the moments when the moon disappeared into the giant planet's shadow and when it emerged again on the other side. After months of careful observation, Rømer noticed something strange. The timing of Io's eclipses drifted throughout the year in a predictable pattern. When Earth's orbit carried it closer to Jupiter, the eclipses occurred earlier than his tables predicted. But when Earth moved to the far side of its orbit, farther away from Jupiter, the eclipses began to arrive late. The discrepancy gradually accumulated to roughly 22 minutes across the full diameter of Earth's orbit around the Sun. Other astronomers initially assumed the drift came from imperfections in the orbital calculations. Perhaps Io's orbit was not quite as regular as previously believed. Perhaps Jupiter's immense gravity produced subtle variations that the models had failed to capture. Rømer considered these explanations carefully and rejected them. The pattern was too consistent and too closely tied to Earth's changing distance from Jupiter. In the year 1676, Römer announced a revolutionary interpretation. The eclipses were not occurring early or late at all. They were happening exactly on schedule. What changed was the time it took for the light-carrying news of each eclipse to reach Earth. When Earth was closer to Jupiter, the light had a shorter distance to travel and arrived sooner. When Earth moved farther away, the light needed more time to cross the increased gap. This meant that light must travel at a finite speed. Römer estimated this speed by dividing the diameter of Earth's orbit by the accumulated delay he observed in the eclipses. His calculation produced a value of roughly 220,000 kilometers per second. That estimate was about 26% too low. Partly because the precise diameter of Earth's orbit was not yet well known, and partly because his timing measurements contained small observational errors. But the scale of the achievement far outweighed these imperfections. Römer had demonstrated something extraordinary. Light was not instantaneous. It traveled at a specific and measurable velocity. Information about distant events required time to reach observers. The universe itself operated with built-in communication delays that depended on distance. This discovery carried profound implications that scientists would only begin to fully appreciate centuries later. If light takes time to travel, then observing distant objects means looking backward in time. The sun we see is the sun as it existed about 8 minutes ago. The universe we observe is therefore a patchwork of different moments in history, each region frozen at a different point in time depending on its distance from Earth. Römer's measurement also revealed something deeply intriguing about the nature of light itself. Its speed was extraordinarily fast, yet fundamentally limited. This limit seemed arbitrary. Why should light travel at exactly this velocity and not some other value? What property of the universe determines this specific number? These questions would haunt physics for the next 2 centuries. While scientists continued refining Römer's measurement with ever-increasing precision, new discoveries gradually sharpened our understanding. In 1728, James Bradley discovered stellar aberration and used it to calculate the speed of light to within about 1% of the modern accepted value. The apparent position of stars shifts slightly as Earth orbits the Sun. The stars themselves are not moving. Instead, Earth's motion changes the angle at which incoming starlight enters our telescopes. This effect depends directly on the ratio between Earth's orbital velocity and the speed of light. By measuring that subtle shift, Bradley could estimate how fast light must be traveling. The first successful terrestrial measurement came much later. In 1849, when Hippolyte Fizeau designed an ingenious experiment using a rapidly rotating toothed wheel, a beam of light passed through a gap between the teeth of the wheel, traveled to a distant mirror, and reflected back toward the source. If the wheel rotated at exactly the right speed, the returning beam would be blocked by the next tooth instead of passing through the original gap. By knowing the rotation rate of the wheel and the distance to the mirror, Fizeau could calculate the speed of light with impressive accuracy. Just 1 year later, in 1850, Léon Foucault improved the method by replacing the toothed wheel with a rotating mirror. His measurements closely matched results from astronomical observations, confirming that light traveled at the same speed whether measured across the solar system or within a laboratory on Earth. Albert Michelson would later refine these rotating mirror techniques to extraordinary precision. His work eventually earned him the Nobel Prize, partly for his meticulous measurements of the speed of light. By the late 19th century, physicists had established the speed of light in a vacuum at approximately 299,792 kilometers per second. The precision of these measurements reached parts per million. This number appeared repeatedly in the equations of electromagnetic theory, always in the same form and always with the same value. Scientists began to suspect that this constant was not merely a property of light, but something far more fundamental about the structure of reality itself. At the time, The prevailing theory treated electromagnetic radiation as waves propagating through a medium known as the luminiferous ether. This invisible substance was believed to fill all of space, permeating the vacuum between planets and stars and providing the medium through which light waves traveled. Just as ocean waves require water and sound waves require air, light waves were thought to require the ether. The ether hypothesis seemed logically necessary. Waves, by definition, are disturbances in some medium. They cannot exist as disturbances in nothing. If light was a wave, then it had to be waving through something. The ether was proposed as that medium, an all-pervasive cosmic substance with unusual and almost contradictory properties. It needed to be rigid enough to support waves traveling at enormous speeds, yet tenuous enough to offer no resistance to planets moving through it. If the ether truly existed, then Earth's motion through this cosmic medium should be detectable. As our planet orbits the Sun at approximately 30 kilometers per second, it would move through the stationary ether like a ship cutting through calm water. Light traveling in the same direction as Earth's motion should effectively appear slower relative to us. Light traveling perpendicular to our motion should remain largely unaffected, and light traveling in the opposite direction should effectively appear faster, pushed along by what would resemble a cosmic tailwind. This so-called ether wind should produce measurable differences in the speed of light depending on the direction in which the light beam traveled. The predicted effect was small, only about 1 part in 10,000. But the precision instruments of the late 19th century were already capable of detecting such subtle variations. The experiment designed to test this prediction would become the most famous failed experiment in the history of science. Albert Michelson was obsessed with precision. He had already built his reputation by measuring the speed of light with unprecedented accuracy. In 1887, he partnered with chemist Edward Morley to construct what would become the most sensitive optical instrument ever built at the time. Their goal was to detect Earth's motion through the luminiferous ether once and for all. The Michelson-Morley interferometer split a beam of light into 2 perpendicular paths using a half-silvered mirror. One beam traveled parallel to Earth's orbital motion, while the other traveled perpendicular to it. Both beams bounced off mirrors and returned to recombine at the half-silvered mirror. If the 2 beams experienced different light speeds because of the ether wind, they would arrive slightly out of phase. This would produce an interference pattern of alternating light and dark bands. Michelson and Morley mounted their apparatus on a massive stone slab floating in a pool of mercury. This ingenious design allowed them to rotate the entire experiment smoothly without vibrations that might disturb the extremely sensitive optics. They could orient the interferometer at any angle relative to Earth's motion and observe whether the interference pattern shifted. The precision of their instrument exceeded the experimental requirements by a comfortable margin. If the ether wind existed at the predicted magnitude, the resulting fringe shift would be clearly detectable. Michelson and Morley conducted measurements at different times of day and in different seasons of the year, sampling various orientations of Earth's motion through space. What they found was deeply surprising. No matter how they rotated the instrument, the interference pattern remained essentially unchanged. Within the precision of their measurement, light seemed to behave the same way in every direction. That quiet result carried enormous consequences, because it suggested that the long-assumed ether might not be there at all. This null result threw theoretical physics into crisis. Light was clearly behaving like a wave, yet waves were believed to require a medium, and the medium that light was supposed to travel through showed no sign of existing at all. Something in the foundations of physics was deeply wrong. Several theorists attempted to rescue the ether hypothesis through increasingly complicated explanations. Perhaps Earth dragged the ether along with it, eliminating relative motion near the surface. Perhaps objects moving through the ether contracted slightly in the direction of motion, exactly compensating for the expected differences in light speed. These ideas could be made to work mathematically, but they felt like desperate patches rather than genuine understanding. The true resolution would come from an unexpected place. A 26-year-old patent clerk in Bern, Switzerland, had been thinking about these puzzles since his teenage years. Albert Einstein approached the problem very differently from his contemporaries. Instead of trying to explain why the ether could not be detected, he asked a much simpler question. What if there was no ether at all? What if light truly traveled at the same speed for every observer? Regardless of how that observer was moving, Einstein later recalled a thought experiment that had troubled him since the age of 16. What would he see if he could chase a beam of light and catch up to it? If he traveled alongside a photon at the speed of light, would the electromagnetic wave appear frozen in place? Would he see a stationary oscillating field suspended motionless in space? Maxwell's equations, which govern electromagnetic phenomena, suggested that this was impossible. Those equations predict that electromagnetic waves must always propagate at one specific speed. They allow no solution for stationary light or for light moving at arbitrary velocities. A frozen electromagnetic wave would violate the mathematical structure that had successfully described every other electromagnetic phenomenon scientists had ever observed. Einstein made a bold decision. Rather than assuming Maxwell's equations were incomplete, or that light behaved differently under extreme conditions, he accepted their prediction exactly as written. Light always travels at the same speed, not because of some special property of light itself, but because of how space and time are structured. In 1905, Einstein published a paper titled On the Electrodynamics of Moving Bodies in the journal Annalen der Physik. The paper was only about 30 pages long. It contained no citations, and it emerged not from a famous university, but from a patent office. Yet it would reshape humanity's understanding of reality itself. Einstein began the paper with two simple postulates that seemed almost obvious. First, the laws of physics are identical in all inertial reference frames. An inertial frame is simply a perspective moving at constant velocity without acceleration. Someone floating freely in space and someone riding on a train moving at a steady speed should observe the same physical laws operating in their environment. Second, regardless of their motion relative to the light source, a beam of light approaches you at the same velocity whether you rush toward it, move away from it, or stand perfectly still. This constancy is not an approximation or an idealization. It is an exact statement about how light behaves. At first glance, these two postulates seem almost trivially true. Of course, the laws of physics should work the same everywhere. And of course, a fundamental constant like the speed of light should truly be constant. But accepting both statements at the same time destroys the intuitive picture of space and time that humans had trusted for thousands of years. To see why, consider what the second postulate really implies. Imagine you are standing still while a beam of light passes you at 299,792 kilometers per second. Now imagine your friend flying toward that same beam of light at half the speed of light, which is about 149,896 kilometers per second. Classical physics would say your friend should measure the light approaching at the sum of those velocities, about 449,688 kilometers per second. Einstein said no. Your friend would still measure the light traveling at exactly 299,792 kilometers per second. The same value you measured, even while moving toward the light at enormous speed. Now imagine your friend turning around and flying away from the light beam at half the speed of light. Classical physics would predict that the light should slowly catch up, appearing to approach at only 149,896 kilometers per second. But Einstein said your friend would once again measure exactly 299,792 kilometers per second. The same speed, no matter how the observer is moving. At first, this seems impossible. How can the same beam of light have exactly the same speed relative to observers moving at completely different velocities? Something must give. Something must adjust in order to make these seemingly contradictory statements compatible. What changes is not the light. What changes are space and time themselves. Einstein showed that space and time are not independent. Absolute quantities, fixed uniformly throughout the universe. Instead, they are deeply intertwined aspects of a single four-dimensional structure called spacetime. Your motion through space affects your experience of time. In order to keep the speed of light constant for every observer, the universe dynamically adjusts measurements of space and time for each observer. The first strange consequence of this is time dilation. Moving clocks run slower than stationary clocks. This is not a mechanical effect or an illusion. Time itself passes more slowly for observers in motion. The faster you move relative to a given reference frame, the slower your time flows compared to that frame. At everyday speeds, this effect is incredibly small and essentially impossible to notice. A commercial airplane flying at about 900 kilometers per hour experiences time dilation of roughly 1 part in 10 trillion. You would need to fly continuously for thousands of years before your watch fell even 1 second behind a clock sitting on the ground. But as speeds begin to approach the speed of light, time dilation becomes dramatic. At 90% of light speed, a moving clock runs at less than half the rate of a stationary clock. 1 full year passing on Earth would feel like only about 5 months for travelers moving at that velocity. And the effect grows even stronger as velocity increases. Time slows more and more dramatically as objects approach the cosmic speed limit. This relationship is described mathematically by a factor physicists call gamma. Gamma equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. When velocity is 0, gamma equals 1. And time flows normally. But as velocity approaches the speed of light, gamma grows larger and larger without limit. At exactly the speed of light, gamma becomes infinite. And when gamma becomes infinite, time effectively stops. A photon traveling at the speed of light experiences no passage of time at all. No matter how far it travels, the billions of years between the moment cosmic microwave background radiation was emitted and the moment one of those photons reaches your eye is, from the photon's perspective, instantaneous. Zero elapsed time. Distance without duration. This is why massless particles can travel at the speed of light, while particles with mass cannot. Photons have zero rest mass. They do not accelerate up to the speed of light. Instead, they are created already moving at that speed. And they cannot exist at any other velocity. A photon cannot slow down. If it somehow lost velocity, it would cease to exist entirely. Photons are fundamentally different from everything else in the universe. They either move at exactly the speed of light, or they do not exist at all. Length contraction is the spatial counterpart to time dilation. Objects in motion shrink in the direction of their movement. A meter stick flying past you at high speed would measure shorter than an identical meter stick at rest. This contraction is not an optical illusion and not a physical compression of the object itself. Space itself changes for observers who are moving. The contraction factor is governed by the same gamma factor that controls time dilation. At 90% of the speed of light, a meter stick would contract to less than half of its original length in the direction of motion. As velocity increases further, the contraction becomes even more dramatic. Objects shrink more and more as they approach the speed of light. Time dilation and length contraction work together in exactly the way required to keep the speed of light constant for all observers. When you move toward a beam of light, your time slows down and your measuring rods contract. These distortions perfectly compensate for your motion. You measure distances differently. You measure time intervals differently. But the ratio between distance and time which defines speed, remains unchanged. The mathematics that describes these relationships is known as the Lorentz transformations. These equations translate measurements between observers moving at different velocities relative to one another. Hendrik Lorentz actually discovered these transformations before Einstein while trying to explain the Michelson-Morley null result through ether-based mechanisms. But Lorentz interpreted his equations as mathematical adjustments, describing how interactions with the ether might affect matter. Einstein revealed that the equations described something far more profound. They were not corrections applied to measurements. They were accurate descriptions of how space and time actually behave. The universe truly does adjust distances and durations depending on the motion of the observer. Lorentz's transformations are not artifacts of measurement. They are the real structure of spacetime itself. From Einstein's framework emerged one of the most famous equations in the history of science. Written with elegant simplicity. Energy equals mass multiplied by the speed of light squared. This equation is often misunderstood as merely a formula explaining nuclear weapons. It does explain why nuclear reactions can release enormous amounts of energy from very small quantities of matter. But the deeper meaning of the equation is far more profound. It tells us that mass and energy are actually the same thing, expressed in different units. The speed of light squared simply acts as the conversion factor between those units. And that conversion factor is enormous. The speed of light squared is approximately 9 times 10 to the power of 16 meters squared per second squared. Multiplying even a tiny amount of mass by this enormous factor produces an extraordinary amount of energy. Just 1 kilogram of matter, if completely converted into energy, would release about 90 quadrillion joules. That amount of energy exceeds the annual energy consumption of a medium-sized country. Mass is essentially concentrated energy. Energy is simply dispersed mass. They are not merely interchangeable under extreme conditions. They are fundamentally the same thing. Different manifestations of a single underlying reality. The speed of light appears in this conversion factor, not because light itself is special, but because the speed of light represents the fundamental relationship between space and time in our universe. This is why the speed of light appears throughout physics. Even in areas that have nothing to do with electromagnetic radiation, it shows up in the equations that describe gravity, particle physics, quantum mechanics, and thermodynamics. In a deeper sense, the phrase speed of light is actually misleading. A more accurate name would be the speed of causality, or the speed of spacetime itself. Light simply travels at this speed because photons are massless. Since Einstein first published his theory of special relativity, scientists have tested it with extraordinary precision. Particle accelerators routinely create particles traveling at more than 99% of the speed of light. These particles experience exactly the time dilation and the increase in momentum that Einstein's equations predict. Every experiment confirms the same conclusion. The speed of light is absolute. Every test shows that space and time adjust themselves in order to maintain this constancy. Relativity is not a theoretical framework waiting to be confirmed. It is an established fact, verified countless times through more than a century of increasingly precise measurements. Yet Einstein's theory describes what happens without fully explaining why. Why is the universe structured this way? Why does space-time possess these particular properties? Why is the speed of light exactly 299,792 kilometers per second? And not some other value? Einstein demonstrated that the speed of light is the cosmic speed limit. He showed how spacetime enforces this limit through time dilation and length contraction. But he did not explain why the universe demands such a limit in the first place. Understanding that deeper reason would require decades of additional work, entirely new mathematical frameworks, and a physicist named Richard Feynman, who could visualize quantum reality in ways no one else had imagined. The answer lies in the quantum mechanical structure of reality itself. At the deepest level, particles do not follow a single path through space. They explore every possible path simultaneously, and the mathematics governing this strange exploration makes faster than light motion not merely difficult or forbidden. It makes it meaningless. The light speed barrier is not a wall-blocking passage. It is a boundary beyond which the concept of motion itself loses coherent meaning. But before we can understand what Feynman discovered about why the speed of light is the ultimate limit, we first need to examine what actually happens as objects begin to approach that barrier. Because the physics of accelerating toward the speed of light reveals layer after layer of impossibility, each one deeper and more fundamental than the last. The barrier is not merely difficult to break. It is mathematically, energetically, and conceptually impenetrable. A gentler way to picture the problem is to imagine a spacecraft that keeps accelerating for a very long time. At first, the relationship between added energy and added speed behaves much as intuition would expect. But as the craft moves faster and faster, each further increase becomes more difficult to achieve. The change is gradual at first, then increasingly severe. By the time the speed approaches that of light, the required energy is no longer merely large. It grows without bound, revealing that the barrier is built into spacetime itself. Einstein's theory of special relativity explains exactly what is happening inside your spacecraft. As your velocity increases, your resistance to further acceleration also increases. Early physicists described this effect as an increase in relativistic mass. The faster you moved, the more massive you effectively became, requiring more force to produce the same acceleration. Modern physicists prefer a slightly different description. They say your rest mass remains constant, but your relativistic momentum increases without limit. Momentum equals mass multiplied by velocity in classical physics. In relativistic physics, momentum equals mass multiplied by velocity multiplied by the gamma factor. As velocity approaches the speed of light, gamma approaches infinity. And so does momentum. The gamma factor deserves careful attention because it governs almost everything strange about relativistic motion. Gamma equals 1 divided by the square root of 1 minus velocity squared divided by the speed of light squared. When you are stationary, gamma equals exactly 1. And physics behaves normally. As you accelerate, gamma begins to increase slowly at first, and then more rapidly. At 50% of the speed of light, gamma equals approximately 1.15. Your effective resistance to acceleration is about 15% higher than it was at rest. Noticeable, but not dramatic. The universe has begun pushing back, but only gently. At 90% of the speed of light, gamma rises to about 2.3. The same thrust that once produced large increases in velocity now produces less than half the effect. You are working much harder for diminishing returns. At 99% of the speed of light, gamma climbs to about 7.1. Every small increase in velocity now costs roughly 7 times more energy than the same increase would require at low speeds. Your engines are now straining against a universe that is increasingly reluctant to let you accelerate further. At 99.9% of the speed of light, gamma exceeds 22. The energy required for each additional increase in velocity has multiplied by more than 20 times compared with what it would cost at rest. You are now burning fuel at phenomenal rates for microscopic gains in speed. At 99.99% of the speed of light, gamma rises above 70. At 99.9999%, it exceeds 220. The pattern continues relentlessly. Every additional 9 added to your velocity multiplies gamma by roughly 3, and each multiplication makes the next increment of speed exponentially more expensive. At exactly the speed of light, gamma becomes infinite. Not an extremely large number, not an approximation, mathematical infinity. The energy required to accelerate any object with mass to precisely the speed of light exceeds any finite quantity. It exceeds the total energy contained in the observable universe. It exceeds the energy of 1 billion observable universes. No amount of fuel, no level of engine efficiency, and no technological breakthrough can overcome mathematical infinity. The Large Hadron Collider demonstrates this principle with astonishing precision. This 27-kilometer ring, buried beneath the border between Switzerland and France, accelerates protons to about 99.999991% of the speed of light. Read those nines carefully. These protons travel at a speed just 7 parts in 10 billion below the speed of light itself. At that velocity, each proton carries kinetic energy comparable to that of a flying mosquito. A mosquito weighs roughly 2.5 milligrams. A proton weighs about 1.7 times 10 to the minus 24 grams. That means a proton is lighter than a mosquito by a factor greater than 1 billion billion. Yet both carry the same kinetic energy because the proton's enormous gamma factor multiplies its tiny mass into something equivalent to the much heavier insect. Now consider what it would take to push those protons, the remaining 7 parts, in 10 billion closer to the speed of light. The energy requirement does not increase gradually. It rises explosively. Closing just half of that remaining gap would already require more energy than the collider currently uses. Closing half of the remaining half would demand even more. Each halving of the remaining distance requires exponentially greater power. To actually reach the speed of light would require infinite energy. The accelerator would need to draw from power sources that do not exist and cannot exist in any finite universe. The barrier is not technological. It is not a problem of funding, engineering, or undiscovered technology. The mathematics of spacetime itself forbids massive particles from ever reaching the speed of light through acceleration. This prohibition appears through several interconnected effects. The requirement of infinite energy is one face of the barrier. Time dilation is another. As your impossible spacecraft approaches the speed of light, time aboard the ship begins to flow differently from time in the universe outside. This is not a malfunction of clocks. And it is not an illusion. Time itself passes more slowly for observers moving at extremely high speeds. At 50% of the speed of light, time dilation is modest. Your shipboard clocks run about 13% slower than clocks on the launch pad back on Earth. For every hour that passes on Earth, only about 52 minutes pass aboard your spacecraft. The difference is measurable, but not dramatic. At 90% of the speed of light, time dilation becomes far more substantial. Your clocks run at less than half the rate of stationary clocks. A year of Earth time compresses into about 5 months of shipboard time. You are aging noticeably slower than the observers you left behind. At 99% of the speed of light, the dilation becomes severe. Your clocks run at roughly 14% of their normal rate. 7 years pass on Earth for every 1 year you experience aboard the ship. The universe outside is aging rapidly, while you move through time in slow motion. At 99.9%, your time slows to about 4.5% of external time. A full century on Earth would pass during less than 5 years of your own experience. Entire civilizations could rise and fall while you completed a single long voyage. As velocity approaches the speed of light itself, time dilation approaches infinity. Time aboard your spacecraft would effectively stop relative to the outside universe. This is a domain that only massless particles can inhabit. Photons exist in this realm of frozen time, but anything with mass is permanently excluded from reaching it. Massive particles face the opposite constraint. They can move at any velocity below the speed of light. From complete rest to 99.99999% of the cosmic limit. But they can never reach the exact speed of light, because doing so would require their time to stop completely. The constraints reinforce one another, creating a barrier that cannot be bypassed. Length contraction offers another way to understand why reaching the speed of light is impossible. As objects accelerate, they contract in the direction of motion. This is not compression in a mechanical sense. The atoms are not being squeezed together by some external force. Instead, space itself contracts for the moving observer. At 50% of the speed of light, an object retains about 87% of its original length in the direction of motion. A 1-meter rod would appear about 87 centimeters long to a stationary observer watching it pass by. At 90% of the speed of light, the contraction becomes far more dramatic. The rod shrinks to about 44% of its rest length. That same 1-meter rod now measures only 44 centimeters to observers who remain at rest. At 99% of the speed of light, the rod contracts to roughly 14 centimeters. At 99.9%, it shrinks to about 4.5 centimeters. And at 99.99%, it would measure only about 1.4 centimeters. The shrinking accelerates as velocity increases. At exactly the speed of light, length contraction would become complete. The rod would have zero length in the direction of motion. It would effectively collapse into a two-dimensional plane with no extension along its direction of travel. For any object that possesses real three-dimensional structure, this represents a physical impossibility. An object cannot have zero thickness in one direction while still containing atoms and occupying volume in the others. Length contraction, time dilation, and the requirement of infinite energy are not three separate barriers. They are three different expressions of the same underlying truth. The geometry of spacetime simply does not contain any path that connects sublight speeds to light speed or faster for objects that have mass. The mathematics is not merely difficult. The mathematics says that such paths do not exist at all. Real experiments confirm every prediction of relativistic mechanics with extraordinary precision. One of the most elegant confirmations comes from muons created in Earth's upper atmosphere. These unstable particles form when cosmic rays collide with air molecules at altitudes of roughly 15 kilometers. Muons have extremely short lifetimes, about 2.2 microseconds. In that brief time, even traveling close to the speed of light, a muon should cover only about 660 meters before half of the population decays. Given their creation altitude and their typical velocities of about 99.94% of the speed of light, muons should decay long before reaching the ground. Classical physics therefore predicts that almost no muons should survive the 15-kilometer journey down to sea-level detectors. Yet ground-based instruments detect enormous numbers of cosmic ray muons, far more than non-relativistic calculations would allow. So where are these extra muons coming from? The answer is time dilation. At 99.94% of the speed of light, the gamma factor is roughly 30. Time passes 30 times more slowly for the muon than it does for observers on Earth. From the muon's own perspective, the journey from its formation altitude down to the ground takes only about 1/30th as long as Earth observers would calculate. Instead of decaying during about 50 microseconds of Earth time, the muon experiences less than 2 microseconds of its own internal time. Most muons survive the journey. Another way to understand this is to examine the situation from the muon's own reference frame. Using length contraction, from the muon's perspective, it is stationary while Earth rushes upward toward it. At 99.94% of the speed of light, Earth's atmosphere contracts by a factor of about 30. The 15-kilometer journey shrinks to only 500 meters. The muon easily survives this much shorter distance before decaying. Both explanations lead to the same prediction. Time dilation in Earth's reference frame and length contraction in the muon's reference frame are mathematically equivalent descriptions of the same physical phenomenon. The number of extra muons detected at ground level matches relativistic calculations with remarkable precision. These predictions are confirmed every day by cosmic ray detectors around the world. Particle accelerators provide even more precise verification. The magnetic force required to bend a particle's path depends on its momentum. At relativistic speeds, momentum increases according to the gamma factor. If momentum followed the rules of classical physics, the magnets used in particle accelerators would need far less strength to guide proton beams. The accelerator would not work at all. The beams would veer off course and smash into the walls of the tunnel instead of circulating smoothly for hours. The magnets are therefore calibrated using relativistic equations. As the protons accelerate, the magnetic fields must increase in strength to compensate for the growing gamma factor. Every adjustment matches the predictions of relativity exactly. If classical physics truly governed particle motion at these speeds, the Large Hadron Collider would be a spectacularly expensive failure. Instead, it works precisely because relativity correctly describes the laws of nature. Even everyday technology quietly confirms these effects. The global positioning system, used by billions of people, depends on relativistic corrections to function properly. GPS satellites orbit Earth at roughly 14,000 kilometers per hour, fast enough to produce measurable time dilation. Their onboard clocks run about 7 microseconds per day, slower than identical clocks on Earth's surface due to velocity effects. Gravitational time dilation introduces an opposing influence. The satellites orbit higher in Earth's gravitational field, where gravity is weaker, and clocks run faster in weaker gravity. This gravitational effect adds roughly 45 microseconds per day compared to clocks on the surface. The combined result is that satellite clocks gain about 38 microseconds per day relative to ground clocks. Without correcting for this discrepancy, GPS position errors would accumulate at roughly 10 kilometers per day. Your navigation system would become unreliable within hours. These corrections work exactly as the equations of relativity predict. They provide everyday confirmation that time dilation is real and that our understanding of it is extraordinarily precise. Given this overwhelming experimental confirmation of relativistic mechanics, some creative thinkers have wondered whether loopholes might exist. Could clever strategies bypass the speed of light barrier, even if direct acceleration cannot? One hypothetical loophole is the concept of tachyons. These theoretical particles would always travel faster than light, just as ordinary matter always travels slower than light. Tachyons would possess imaginary rest mass, a mathematical property that reverses the usual relationship between energy and velocity. While ordinary particles require infinite energy to reach the speed of light from below, tachyons would require infinite energy to slow down to the speed of light from above. The idea seems elegant at first. Perhaps the universe contains two classes of particles separated by an unreachable boundary. Ordinary matter would exist below the speed of light, while tachyons would exist above it, with neither able to cross into the other's domain. The difficulty with this idea is causality. In the framework of special relativity, traveling faster than light is mathematically equivalent to traveling backward in time. Different observers moving at different velocities would disagree about whether a tachyon traveled forward or backward in time. For some observers, a tachyon message could arrive before it was even sent. This creates causal loops that destroy logical consistency. You could receive information about future events and then use that information to change them. You might prevent the very causes that led to receiving the message in the first place. You could even observe your own departure from the perspective of having already arrived. The contradictions multiply without resolution. These are not philosophical puzzles open to interpretation. They are logical impossibilities that break the mathematics required for consistent physical laws. A universe that allowed faster than light travel would be a universe without reliable causality. Effects could occur before their causes. Information could erase itself by preventing its own creation. Yet, every experiment ever performed shows that our universe does not behave this way. Causality unfolds in a consistent order from past to future. Causes precede effect, and information moves forward through time, never backward. The speed of light enforces this structure by preventing any causal connection between events that are separated in spacetime in a way that would allow faster-than-light influence. No experiment has ever detected a tachyon, No theoretical framework has successfully incorporated such particles without producing paradoxes. The overwhelming weight of evidence suggests that tachyons are mathematical curiosities, not physical realities. Another apparent loophole comes from quantum tunneling. In quantum mechanics, particles sometimes appear on the far side of barriers that they should not be able to cross according to classical physics. An electron approaching a wall that is too tall and too thick to climb can occasionally be found on the other side. In quantum mechanics, the particle does not climb over the barrier or slip around it. Instead, it can appear on the other side through quantum tunneling. This raises a fascinating question. Could particles also tunnel through the light-speed barrier? Could quantum mechanics somehow provide an escape from the restrictions imposed by relativity? Careful analysis shows that it cannot. Quantum tunneling does not actually transmit anything faster than light. The confusion comes from the way physicists measure tunneling times. A quantum particle approaching a barrier is not a tiny billiard ball. It behaves as a wave packet spread out in space, with a leading edge, a central peak, and a trailing edge. When part of this wave packet tunnels through a barrier, the transmitted wave becomes reshaped. Because of this reshaping, the center of the transmitted packet can appear beyond the barrier before the entire front of the incoming packet has entered it. This creates the illusion of superluminal motion. The peak of the outgoing wave seems to appear on the far side before the peak of the incoming wave even reaches the barrier. At first glance, it looks as though the particle has traveled faster than light. But this interpretation is misleading. Information is not carried by the peak of the wave packet. Information travels with the front edge of the wave. And that leading edge never emerges sooner than relativity allows. No signal, messenger, or information of any kind travels faster than light through quantum tunneling. The apparent faster-than-light effect is therefore an artifact of wave mechanics, not a real violation of relativistic limits. Experiments in the 1990s tested this directly. Researchers sent photons through carefully designed barriers and measured their tunneling times with extraordinary precision. Some early results appeared to suggest faster-than-light propagation. However, deeper analysis later showed that these measurements were fully consistent with relativity once the reshaping of the wave packet was properly understood. Closer analysis eventually revealed the truth. The front edge of the transmitted wave packet, which is the part that carries actual information, always obeys causality. The reshaping of the wave packet only made it appear as though the packet's center arrived earlier than expected. In reality, this was simply a measurement artifact, not genuine faster-than-light travel. Quantum mechanics therefore respects the speed of light limit just as strictly as classical relativity does. Another idea proposed to bypass this barrier is the Alcubierre warp drive. In 1994, physicist Miguel Alcubierre suggested that a spacecraft might not need to travel faster than light locally in order to cross vast cosmic distances faster than light could travel through normal space. The concept works by contracting spacetime in front of the spacecraft and expanding it behind. The ship would effectively ride inside a wave of distorted spacetime, remaining stationary relative to the space immediately around it. From the ship's perspective, it never exceeds the speed of light. However, the region of spacetime containing the ship could move faster than light relative to distant observers. In this way, the craft could cover superluminal distances without violating the local laws of relativity. The mathematics of general relativity technically allows solutions like this. Spacetime can bend, stretch, and distort in response to mass and energy. Nothing in the equations directly forbids the kind of metric Alcubierre described. The real problem lies in the energy requirements. Creating such a warp bubble would require exotic matter with negative energy density, capable of producing gravitational repulsion instead of attraction. Quantum physics does allow very small amounts of negative energy to appear under special circumstances. but the amount required for even a modest warp bubble would exceed the total positive energy contained in the observable universe. More recent analyses reveal additional difficulties. The forward edge of a warp bubble would accumulate particles and radiation as it moved, compressing them into catastrophically high densities. When the bubble stopped, that stored energy could be released in a devastating burst. In other words, even if the warp drive were theoretically possible, the physics required to build and control such a system remains far beyond anything our current understanding of the universe can realistically support. When such a warp bubble reached its destination and collapsed, the accumulated particles and radiation at its leading edge would be released in a violent burst of energy. In extreme scenarios, this discharge could be powerful enough to sterilize an entire star system. There is another practical problem as well. Passengers inside the warp bubble would not be able to control or steer it. Signals from inside the bubble cannot reach its outer boundary faster than light, which means the occupants would have no way to influence the bubble's motion once it formed. For these reasons, the Alcubierre warp drive remains a mathematical curiosity, not a realistic propulsion system. No known physics allows the creation of the exotic matter required for such a structure, especially not in the enormous quantities needed. Another theoretical idea often discussed is the concept of wormholes. These hypothetical tunnels through spacetime could connect two distant regions of the universe. Instead of traveling across the immense distance between stars, a spacecraft could enter one mouth of a wormhole and emerge from the other mouth light years away, effectively bypassing the intervening space. Wormholes appear in certain solutions of general relativity, originally developed by Albert Einstein. The mathematics of the theory does not forbid their existence. However, a traversable wormhole, one that stays open long enough for something to pass through, would require exotic matter with negative energy density. The same hypothetical substance required by the Alcubierre warp drive, natural wormholes, if they exist at all, would likely appear only as microscopic quantum fluctuations, far too small for a spacecraft or even a single particle to pass through. Expanding such a structure to a usable size would require forms of physics and energy manipulation that humanity cannot achieve and may never be able to achieve. Every proposed loophole runs into the same ultimate barrier. The speed of light is not merely a technological limitation. It is a fundamental property of how spacetime connects events in the universe. There are no paths through spacetime that connect velocities below the speed of light to velocities at or above the speed of light for objects with mass. The barrier exists not because something actively blocks the crossing. The barrier exists because there is simply no physical state on the other side that massive objects can reach. Albert Einstein showed that this barrier is built directly into the mathematical structure of the universe. His equations describe exactly what happens as objects accelerate toward the speed of light. They reveal the asymptotic nature of the limit. The closer an object gets to light speed, the more energy is required, rising without bound. Every experiment performed over the past century confirms these predictions with remarkable precision. Particle accelerators, cosmic ray observations, and satellite systems all behave exactly as relativity predicts. Yet Einstein's theory leaves a deeper question unanswered. It explains how the speed limit works, but not why spacetime itself has this structure. Why is there a cosmic speed limit at all? Why is that limit exactly 299,792 kilometers per second? What makes this particular velocity so special that the entire fabric of reality enforces it? Answering these questions requires looking deeper than special relativity alone. The explanation begins to emerge from quantum mechanics, the theory that describes how particles behave at the smallest scales of nature. A crucial insight came from the work of Richard Feynman. His revolutionary approach to physics revealed that the speed of light is not simply an external rule imposed on the universe. Instead, it emerges naturally from the most fundamental principles governing how particles move through spacetime. In this view, The light speed limit is not a wall that objects collide with. It is a consequence of the deeper quantum structure of reality itself. Richard Feynman arrived at Princeton University in the autumn of 1939, already carrying a reputation that preceded him. The 21-year-old student from Far Rockaway in New York had already shown an unusually intuitive relationship with physics. Even at that early stage, it was clear that he saw the universe in ways that few others could. While other students memorized formulas and followed prescribed methods, Richard Feynman approached physics in an entirely different way. Instead of relying on established procedures, he often rebuilt solutions from the ground up. He trusted his intuition more than textbooks. Where others filled pages with equations, he preferred drawing pictures and imagining how physical processes unfolded in space and time. He asked questions that sometimes made professors uneasy because they challenged assumptions that most people simply accepted. His doctoral advisor, John Archibald Wheeler, quickly realized that something unusual was happening in the mind of this young student. Feynman was not just talented at solving problems. He seemed to see physics differently from everyone around him. Many physicists at the time treated their work as an exercise in abstract mathematics. They manipulated symbols and equations to reach conclusions. Feynman, however, visualized physical events unfolding in reality. Instead of imagining symbols on paper, he imagined particles moving, colliding, and exchanging energy across spacetime. This visual approach would eventually open the door to one of the deepest insights in modern physics. The question was not simply what happens when objects approach the speed of light. The deeper question was why the universe enforces this limit with such precision. The insight that Feynman helped reveal did not introduce new rules to physics. Instead, it suggested something far more profound. The speed of light limit was never an arbitrary rule imposed on the universe. It emerged naturally from the fundamental structure of reality itself. When Feynman began his graduate research, he inherited a problem that seemed almost impossible to solve. The theory describing the interaction between light and matter, known as quantum electrodynamics, was deeply flawed. Physicists in the 1920s and 1930s had already developed the basic framework of the theory. They understood that charged particles such as electrons interact by exchanging photons. The quantum particles of light. The equations describing these interactions were known. But when researchers tried to use those equations to calculate real physical quantities, they encountered a disturbing problem. The results often became infinite. Consider the simplest possible case. Imagine calculating the energy of a single electron sitting alone in empty space. The electron creates an electromagnetic field around itself, and that field carries energy. When physicists attempted to calculate the total energy of that field using the existing equations, the answer did not come out as a large number. It came out as infinity, a result that clearly made no physical sense. The electromagnetic field around an electron contains energy, and the electron interacts with its own field in ways that affect its measurable properties. When physicists attempted to calculate this self-energy using the equations of quantum electrodynamics, they encountered a shocking result. When physicists tried to calculate certain quantities in early quantum electrodynamics, the theory stopped giving sensible finite answers. Instead, the mathematics kept running away from them. That was a serious problem, because the measured properties of electrons are clearly finite and well-behaved in experiments. So the challenge was not simply to do a harder calculation. It was to understand why a successful theory of nature could produce answers that, in raw form, no longer matched physical reality. Some physicists concluded that the entire framework must be flawed. Perhaps quantum mechanics could not be reconciled with the principles of relativity. Perhaps a completely new theory of physics would be required to replace both. This crisis persisted through much of the 1930s. While the world itself moved toward global conflict and many of the brightest physicists were scattered across different countries. During the war years, Richard Feynman worked at Los Alamos Laboratory as part of the Manhattan Project. Even while contributing to wartime research, his mind continued to return to unresolved theoretical questions. After the war ended, Feynman returned to academic life at Cornell University. There he began attacking the infinity problem with renewed determination and with the unconventional style that had always defined his thinking. The eventual breakthrough did not come from one physicist alone. It emerged from parallel efforts by Feynman, Julian Schwinger at Harvard, and Shinichiro Tomonaga in Japan, working independently but toward the same goal. They developed a method that would rescue the theory from its infinities and transform quantum electrodynamics into one of the most precise scientific theories ever created. They developed a method known as renormalization, a procedure that allowed physicists to extract meaningful finite results from equations that initially produced infinities. The infinities themselves did not disappear. Instead, they were absorbed into the definitions of measurable physical quantities, such as mass and electric charge. The reasoning behind this approach was subtle but extremely powerful. When we measure the mass of an electron, we are not observing an isolated object. We are measuring the electron together with the electromagnetic field that surrounds it. The electron constantly interacts with that field, and those interactions influence the value we measure. The infinite self-energy that appears in the calculations becomes part of the quantity we call the electron's mass. Rather than trying to compute that contribution from first principles, physicists simply use the experimentally measured mass, which already includes all of these effects. In this way, the troublesome infinities were absorbed into quantities determined directly by experiment rather than by calculation. The equations then produced finite predictions that could be compared with observations. Mathematically, renormalization worked extraordinarily well. Yet many physicists remained uneasy about it. Philosophically, it seemed as though the infinities were merely being hidden rather than explained. Even Richard Feynman himself felt some discomfort with the idea. Despite using the technique with remarkable success, but his contribution to the theory went far beyond renormalization. Feynman developed an entirely new way of formulating quantum mechanics that revealed deeper insights into how nature actually works. He called this approach the path integral formulation, which later became widely known as the sum over history's interpretation. In classical physics, motion is described by a single deterministic trajectory. Imagine throwing a baseball across a field. Once the starting conditions are known, its path through space can be calculated precisely. The laws of physics determine exactly where the ball will be at every moment along its flight. Feynman suggested that quantum particles behave in a completely different way. An electron traveling from one point to another does not follow a single well-defined path. Instead, it behaves as if it explores every possible path through spacetime simultaneously. An electron moving from one point to another does not follow a single trajectory. According to the picture developed by Richard Feynman, the particle behaves as if it explores every possible path simultaneously. Every conceivable trajectory connecting the starting point and the destination contributes to the particle's behavior. Straight paths, curved paths, paths that wander unpredictably, and even paths that loop around through distant regions of space all contribute in principle. At first, this idea sounds almost mystical. How can a single particle follow infinitely many routes at once? The answer requires abandoning classical intuition and accepting one of the central ideas of quantum mechanics: the principle of superposition. Before a measurement occurs, a quantum particle does not possess a definite trajectory. Instead, it exists in a superposition of all possible paths connecting the initial and final points. Each of these paths contributes to the particle's behavior through something known as a probability amplitude. A probability amplitude is a complex number containing both magnitude and phase. The magnitude describes how strongly a particular path contributes, while the phase determines how that contribution combines with contributions from other paths to predict an observable outcome, such as the probability that an electron arrives at a particular location. Physicists must add together the amplitudes associated with all possible paths. Because these amplitudes have phases, they can combine in different ways. Some contributions reinforce each other through constructive interference, while others cancel through destructive interference. This is the key point where familiar classical behavior begins to emerge from the strange mathematics of quantum mechanics. Paths that wander wildly through space tend to have phases that change rapidly. When the contributions from many such paths are added together, their rapidly shifting phases cause them to cancel each other out. As a result, only a small set of paths contribute significantly to the final outcome, producing the appearance that particles follow well-defined trajectories, even though, at the deepest level, every possible path was considered. The wild detours through distant regions of the universe contribute almost nothing to the final probability. Their phases vary so rapidly that they cancel each other through destructive interference. As a result, those bizarre routes effectively disappear from the calculation. Paths that remain close to the classical trajectory behave differently. Their phases change slowly and remain aligned with one another. Because of this alignment, their contributions add constructively instead of cancelling out. The electron is therefore most likely to appear near the location predicted by classical physics. This does not happen because quantum mechanics forces the particle to follow a single path. It happens because the classical trajectory is the region where many similar paths reinforce each other. Richard Feynman showed that this path integral description is mathematically equivalent to the traditional approach based on the Schrödinger equation. Both frameworks produce identical predictions for every experiment ever tested. Yet Feynman's formulation offers a completely different way of thinking about what quantum particles are actually doing. Instead of following a single trajectory, particles behave as if they explore every possible history connecting two events. This perspective also reveals something profound about the speed of light limit. It shows that the limit is not an arbitrary rule inserted into physics. Instead, it arises naturally from the mathematical structure that governs how particles move through spacetime. In the path integral framework, the contribution from each possible path depends on a quantity known as the action. The action is obtained by integrating another quantity called the Lagrangian along the path the particle takes through spacetime. For relativistic particles, the Lagrangian depends on how the particle moves through both space and time. Within this relationship, the speed of light appears as the fundamental constant that links spatial motion with the flow of time itself. In other words, the light speed limit emerges directly from the geometry of spacetime and the quantum rules governing particle motion, rather than from any external restriction imposed on the universe. When a possible path includes any segment where a particle would move faster than the speed of light, something remarkable happens to its contribution. The action associated with that segment becomes imaginary rather than real. In the framework introduced by Richard Feynman, this change has dramatic consequences. An imaginary action causes the phase of the probability amplitude to oscillate infinitely rapidly along the faster-than-light portion of the path. When a phase oscillates infinitely fast, the contributions from nearby paths cancel perfectly through destructive interference. In other words, paths that contain faster-than-light motion cancel each other out with absolute precision. Mathematically, they still appear in the sum over all possible histories. But physically, they contribute exactly zero to any observable outcome. This provides a deep quantum explanation for why nothing travels faster than light. The universe does not enforce the limit through external rules or cosmic restrictions. Instead, the mathematical structure of quantum mechanics automatically eliminates any contribution from superluminal motion. Paths that exceed the speed of light simply interfere themselves out of existence. This insight changed how physicists interpret the light speed barrier. Albert Einstein had already shown that approaching the speed of light requires infinite energy and produces extreme time dilation. Those infinities suggested an impenetrable boundary. However, Einstein's work described the consequences of the limit rather than the underlying reason for it. Feynman's perspective revealed something deeper. The barrier is not imposed externally on the universe. It emerges naturally from the way probability amplitudes combine in quantum mechanics. The rules that determine how amplitudes add together already contain the speed limit within them. No additional constraint needs to be enforced. The mathematics itself ensures that faster-than-light contributions cannot survive the summation process that determines physical reality. Consider the deeper implication of this idea. The speed of light limit is not simply a restriction placed on otherwise possible motion. It reflects something more fundamental about how motion exists at the quantum level. Paths that would require faster-than-light travel do not contribute to physical reality because their contributions cancel completely. In this sense, asking how to travel faster than light becomes almost meaningless. There is no faster-than-light path within the quantum sum that could be enhanced or exploited. Such paths mathematically appear in the calculation, but they vanish through perfect destructive interference. To make these ideas practical, Richard Feynman introduced a powerful visual tool known as the Feynman diagram. These diagrams appear simple at first glance, but they encode extremely complex mathematical expressions in a visual format. They allow physicists to calculate interactions between particles without writing pages of complicated algebra. In a Feynman diagram, particles are represented by lines moving through spacetime, while interactions occur at points where those lines meet. Known as vertices, time is usually represented as flowing upward or toward the right, while space extends in directions perpendicular to that flow. Each line corresponds to a particle propagating through spacetime, and each vertex represents a moment where particles interact, are created, are destroyed, or exchange energy. For example, when an electron emits a photon, the diagram shows a straight electron line with a wavy photon line branching outward from a vertex. The electron continues beyond that point with slightly different momentum because it has transferred some of its energy and momentum to the departing photon. The reverse process represents photon absorption. In that case, a photon line approaches and merges with an electron line at a vertex, after which the electron continues with increased energy and momentum. The electromagnetic force between two electrons can also be visualized in this way. Two electron lines move roughly parallel through spacetime, and a wavy photon line connects them. That photon represents a quantum of electromagnetic energy exchanged between the electrons. By transferring momentum from one electron to the other, it causes their paths to deflect, producing what we recognize as the electromagnetic interaction. At the quantum level, this exchange of photons explains why electrons repel one another. The interaction is not a continuous force in the classical sense. Instead, it arises from the exchange of quantum particles that transfer energy and momentum between them. In the framework developed by Richard Feynman, each Feynman diagram corresponds to a precise mathematical expression. The set of instructions used to translate these diagrams into equations are known as Feynman rules. Using these rules, physicists convert each diagram into a probability amplitude. By drawing every possible diagram describing a given interaction, translating them into mathematics, and adding their contributions together, researchers can calculate the probability of any interaction predicted by quantum electrodynamics. Before this method existed, such calculations were incredibly difficult and often required years of effort. After Feynman introduced his diagrams, problems that once demanded massive algebraic work could be solved by graduate students with pencil and paper. The diagrams did not change the underlying physics. Instead, they made the physics understandable and calculable. They also revealed something deeper about the nature of quantum interactions. The photons exchanged between electrons in these diagrams are known as virtual photons. These differ fundamentally from the real photons that reach our eyes or trigger detectors in experiments. Real photons must obey a strict relationship between energy and momentum determined by their zero mass. For a real photon, once the energy is known, the momentum is fixed by the laws of relativity. Virtual photons are different, because they exist only temporarily inside a quantum interaction. They are not bound by the same constraints. A virtual photon can carry combinations of energy and momentum that would be impossible for a real photon. It may appear to have more momentum than its energy would normally allow, or less. In some calculations, it may even appear to carry energy with the opposite sign. These unusual properties do not violate physical law because virtual particles are not directly observable objects. They are mathematical elements inside the quantum calculations that describe how real particles interact. At first, this freedom seemed troubling. If virtual particles could carry combinations of energy and momentum that real particles could never possess, it looked as though the theory might violate fundamental conservation laws. Some critics argued that Feynman diagrams were merely mathematical tricks rather than genuine descriptions of physical reality. How could particles exist with energies or momenta that appear impossible? Richard Feynman clarified that virtual particles are not physical objects in the ordinary sense. They are elements within the mathematical framework that describe how quantum fields interact and transmit forces. The unusual energies and momenta assigned to virtual particles do not appear in the final observable result. When all possible contributions are summed together, these intermediate inconsistencies cancel out. What remains after the full calculation respects every conservation law and every physical constraint, including the speed of light limit. This insight also explains an important point about faster-than-light motion. Within the intermediate steps of a calculation, virtual particles can mathematically appear to move faster than light. However, when all contributions are combined to produce a measurable outcome, no information ever travels faster than light. The temporary superluminal behavior exists only inside the mathematics of the calculation. It never appears in the final physical prediction. Consider two electrons repelling each other by exchanging virtual photons. The electromagnetic interaction between them does not occur instantaneously across space. If one electron suddenly changes its motion, the second electron does not respond immediately. The electromagnetic field connecting them updates at exactly the speed of light. Information about the change in motion propagates through the field at that speed and no faster. Even though the intermediate mathematical description may include virtual particles with unusual properties, the final outcome always respects the fundamental structure of spacetime described by special relativity. This principle extends throughout the entire framework of quantum field theory. The mathematics may allow strange intermediate steps, but the observable predictions always preserve causality and the universal speed limit set by the structure of spacetime. Virtual particles can appear to violate the rules that constrain real particles. However, the quantities we can actually observe and measure always obey the fundamental limits of physics, including the speed of light. The mathematics of quantum theory works in such a way that causality is never violated in any measurable process. These ideas become clearer within the framework of quantum field theory. In this view, particles are not tiny objects flying through empty space like billiard balls. Instead, they are localized excitations of fields that exist everywhere throughout spacetime. The electromagnetic field, for example, fills all of space. When that field vibrates in a particular way, the vibration appears to us as a photon. The photon is not an independent object traveling through the field. The photon is simply the electromagnetic field oscillating. The same principle applies to matter. The electron is associated with a field that also exists everywhere. An electron is a localized disturbance within that electron field rather than a separate object placed inside it. This perspective helps explain why photons move exactly at the speed of light, while electrons move more slowly. The electromagnetic field has no mass. The equations describing that field allow disturbances to propagate only at one specific speed. The speed of light. Not faster and not slower. A photon must therefore move at the speed of light because that is the only speed at which disturbances in the electromagnetic field can travel. The electron field is different because it includes a mass term in its governing equations. That mass restricts how disturbances in the field propagate. As a result, an electron can move at many possible speeds, but always below the speed of light. The presence of mass prevents the electron from reaching that limit. The heavier the particle associated with a field, the more strongly its motion is restricted to speeds lower than the cosmic limit set by the structure of spacetime. This relationship between mass and propagation speed is not imposed by an external rule. It emerges naturally from the mathematical structure of relativistic quantum field theory. When physicists write equations that obey both quantum mechanics and special relativity, the speed of light appears automatically as a fundamental limit. For fields with no mass, disturbances propagate exactly at the speed of light. For fields associated with massive particles, motion can approach that speed but never reach it. The speed of light therefore appears as the maximum possible propagation speed for massless fields and as an asymptotic limit for massive ones. Physicists, such as Richard Feynman, showed that this structure is not optional. Any quantum field theory that is consistent with special relativity must obey these constraints. Whenever researchers attempt to construct theories that allow faster-than-light propagation, the mathematics begins to break down. Probability conservation fails. Causal relationships become inconsistent. And paradoxes appear. The equations themselves lose internal coherence. The only theories that remain logically consistent are those in which the speed of light emerges as the maximum speed at which causal influence can travel. This is not an extra rule added to the theory. It is a requirement for the mathematics to remain meaningful at all. In that sense, the light speed limit is woven directly into the foundations of quantum reality. At first glance, however, quantum entanglement seems to challenge this conclusion. Two particles that interact can become entangled so that measuring one instantly reveals information about the other, even if they are separated by enormous distances. This strange behavior disturbed Albert Einstein so much that he famously described it as spooky action at a distance. Einstein suspected that such behavior meant quantum mechanics was incomplete. Yet, entanglement does not actually allow information to travel faster than light. The correlations between entangled particles appear instantly, but they cannot be used to send messages. When one particle is measured and its spin is found to point in one direction, the partner particle will be measured with the opposite spin, even if that partner lies on the far side of the galaxy. The correlation appears immediate, but no controllable signal travels between the particles. Because of this, the cosmic speed limit imposed by relativity remains intact. The crucial subtlety lies in what can actually be done with this correlation. Quantum entanglement creates a connection between distant particles, but that connection cannot be used to send a message. When you measure your local particle, the result is random. Its spin may be up or down with equal probability. The distant particle will show the opposite result. But from the perspective of the observer measuring it, the outcome also appears completely random. To realize that the two results are correlated, the observers must later compare their measurements. That comparison requires ordinary communication, which can travel no faster than the speed of light. The correlation itself appears instantly, but knowledge of the correlation spreads only at light speed or slower. No usable information ever exceeds the cosmic limit. Physicists have proven this mathematically through what is known as the no-communication theorem. This theorem demonstrates that quantum mechanics preserves causality, even though entangled systems display non-local correlations. Entanglement links distant particles in remarkable ways. But those connections cannot carry messages faster than light and cannot transmit information backward in time. This preservation of causality is not an accident. The mathematical structure of modern quantum field theory requires it. Any theory that allowed faster-than-light signaling would produce contradictions and logical paradoxes. Quantum mechanics, therefore, approaches the boundary of causality with its instantaneous correlations. But it stops precisely at the point where a true violation would occur. The ultimate expression of the light speed limit appears in one of the most extreme objects in the universe: the black hole. Black holes form when enormous amounts of mass collapse into an extremely small region of space. The gravitational pull becomes so strong that the escape velocity at the surface reaches the speed of light. Because nothing can travel faster than light, nothing that crosses that boundary can escape again. That boundary is known as the event horizon. The event horizon is not a physical surface. There is no wall or membrane marking its boundary. Instead, it is a causal boundary within spacetime, a surface beyond which events can no longer influence the outside universe. Light emitted just inside the horizon still travels outward at the speed of light. Yet it makes no progress against the intense curvature of spacetime created by the black hole. The outward motion of the light is exactly balanced by the inward flow of spacetime itself. As a result, the light remains trapped. From the outside, it appears to approach the horizon endlessly without ever escaping. For a distant observer, objects falling toward a black hole never seem to cross the horizon. As they approach it, the effects of gravitational time dilation become increasingly extreme. The falling astronaut appears to slow down. Their light becomes increasingly redshifted and faint. Eventually they fade from view entirely, appearing almost frozen near the boundary. Yet from the astronaut's own perspective, the crossing happens normally and in a finite amount of time. They pass through the horizon without encountering any physical surface. But once that crossing occurs, they have moved beyond the region of spacetime that can communicate with the rest of the universe. Inside the horizon, the structure of spacetime changes in a dramatic way. The singularity at the center of the black hole is no longer a location you might travel toward or avoid. Instead, it lies in the future of every possible path within the horizon. No matter which direction you move, every trajectory leads inevitably toward the singularity. The singularity is not a place in space you could steer away from. It is a moment in the future that cannot be avoided. Because nothing can move faster than light. Escaping the interior of a black hole would require traveling along a path that effectively moves backward in time relative to the geometry of spacetime. The speed of light limit therefore becomes the ultimate barrier. Once inside the event horizon, the causal structure of spacetime ensures that escape is impossible. This deep connection between event horizons and causality reveals something profound about the cosmic speed limit. The speed of light is not simply a number describing how fast light travels. It defines the very structure of cause and effect throughout the universe. Black holes are extreme demonstrations of how causality shapes the geometry of spacetime. The same speed of light that prevents messages from traveling backward in time also prevents anything from escaping the interior of a black hole. The same causal structure that gives time its direction also creates regions of spacetime that are permanently isolated from the rest of the universe. Physicists have proposed an idea known as the cosmic censorship conjecture. According to this conjecture, singularities never appear naked to the outside universe. They remain hidden behind event horizons, safely concealed from external observers. If this idea is correct, the speed of light limit plays an additional role in protecting the universe from the extreme mathematical pathologies associated with singularities. Causality would maintain cosmic order by ensuring that the most violent gravitational phenomena remain forever hidden from direct observation. Black holes therefore stand as cosmic monuments to the speed of light limit. They mark locations where causality creates absolute barriers in spacetime. No technology, no matter how advanced, could retrieve information from within an event horizon. The cosmic speed limit has carved permanent voids into the structure of existence, regions as inaccessible as events that lie outside our light cones in spacetime. The theoretical framework developed by Richard Feynman and others has been tested with extraordinary precision. The theory known as quantum electrodynamics remains one of the most accurate scientific theories ever constructed. One of the most striking tests involves a property of the electron known as its magnetic moment. Often described through a quantity called the G factor, classical physics predicted that an electron spinning within a magnetic field should have a G factor equal to 1. Later developments in early quantum theory revised that prediction to exactly 2. Both predictions came close to the measured value but did not match experiments perfectly. Quantum electrodynamics provided the missing corrections. These corrections arise from the electron's interaction with virtual photons within its own electromagnetic field. A subtle effect, predicted by the quantum structure of the theory. When these corrections are included, the theoretical prediction matches experimental measurements with astonishing precision, confirming that the underlying framework describing light, matter, and their interactions is extraordinarily accurate. The more diagrams physicists include in their calculations, the more precise the predictions become. Researchers have pushed these calculations to extraordinary levels of detail, including contributions from diagrams containing up to 5 loops of virtual photons. Performing these calculations is enormously complex. It requires evaluating tens of thousands of individual Feynman diagrams, each representing a different possible quantum interaction. When all of these contributions are combined, the theoretical prediction matches experimental measurements with astonishing precision. The agreement reaches better than 1 part in a trillion. To understand how precise that is, imagine measuring the distance from New York to Los Angeles using a ruler accurate to 1 part in a trillion. Your result would be correct to within the width of a single atom. This is the level of agreement achieved by quantum electrodynamics. No other theory in the history of science has been tested with such precision and confirmed so thoroughly. Quantum electrodynamics is not merely approximately correct. Within the limits of our current ability to measure and calculate, it is exactly correct. Every prediction it makes, including the absolute nature of the speed of light limit, has been verified beyond reasonable doubt. Modern particle physics extends this framework through the Standard Model. This theory includes not only photons and electrons, but also quarks, neutrinos, the Higgs boson, and the particles responsible for the weak and strong nuclear forces. The entire structure relies on the mathematical ideas that Richard Feynman helped develop, especially the path integral formulation of quantum mechanics. Within this framework, every interaction between particles respects the same fundamental constraint. Information never propagates faster than the speed of light through any known quantum process. Causality is preserved in every prediction that has been tested experimentally. The cosmic speed limit is not a special rule that applies only in certain situations. It emerges naturally from the mathematical structure of quantum field theory, the framework that describes all known fundamental interactions. Within this framework, the strength of electromagnetic interactions is determined by a remarkable number known as the fine structure constant. This constant, usually written as alpha, has a value close to 1 divided by 137. The fine structure constant determines how strongly electrons interact with photons. It appears throughout the equations of quantum electrodynamics, influencing everything from the structure of atoms to the forces between electrically charged particles. Richard Feynman often spoke about this number with a sense of awe. Its value cannot currently be derived from deeper theoretical principles. Instead, it must be measured experimentally. Yet this single-dimensionless constant, together with the masses of fundamental particles, determines the entire character of electromagnetic interactions across the universe. If the fine structure constant were significantly larger, electromagnetic forces would become stronger, atoms would shrink, and the behavior of chemistry would change dramatically. Under such conditions, the complex chemistry required for life might never arise. If the constant were significantly smaller, electromagnetic forces would weaken, atoms would become larger and less tightly bound. Chemical reactions would behave differently, potentially making the formation of stable molecules far more difficult. Again, the emergence of life as we know it could become impossible. This constant is deeply connected to the speed of light through the fundamental equations that govern electromagnetic interactions. It reflects how the properties of charge, quantum mechanics, and the structure of spacetime combine to shape the physical laws that operate throughout the universe. Both quantities appear together in the equations that describe how charged particles interact. The speed of light determines the maximum speed at which influences can propagate through spacetime. The fine structure constant determines how strongly charged particles interact with the electromagnetic field. Together, these two quantities shape the behavior of electromagnetic phenomena across every scale of the universe. From the smallest interactions between elementary particles to the largest structures observed in astrophysics. Richard Feynman often emphasized that the fine structure constant remains one of the deepest mysteries in physics. Its value is enormously important for the structure of matter and the behavior of atoms. Yet its origin cannot currently be derived from deeper theoretical principles. It must be measured experimentally. Feynman once described it as a number that clearly matters profoundly for the universe, but whose underlying explanation remains completely unknown. Understanding why fundamental constants take the specific values we observe remains one of the open challenges of modern theoretical physics. What Feynman did demonstrate with mathematical clarity is that the speed of light limit is not an independent rule added to the laws of nature. It emerges naturally from the same quantum field theory structure that governs particle interactions. The very framework that predicts the electron's magnetic properties with extraordinary precision also explains why faster-than-light motion never appears in physical reality. The cosmic speed limit is therefore not a restriction imposed on the universe from outside. It arises because the universe is built from quantum fields that must obey the principles of relativity. Within this framework, there is no separate domain beyond the light-speed boundary waiting to be accessed. Motion faster than light does not appear as a consistent possibility within quantum field theory. It simply does not exist as a coherent concept in the structure of the laws that govern our universe. Richard Feynman approached physics with a mixture of playful curiosity and uncompromising rigor. He once remarked that if someone believes they truly understand quantum mechanics, then they probably do not understand it at all. Feynman embraced the strange and counterintuitive nature of the quantum world. At the same time, he insisted that every idea must be grounded in precise mathematics and confirmed through experiment. His path integral formulation was not simply a clever technique for simplifying difficult calculations. It revealed something deeper about the structure of reality. Through this approach, it became clear that quantum mechanics and special relativity fit together in a very specific way. When the two frameworks are combined consistently, the speed of light limit appears automatically. The apparent barrier at the speed of light is therefore not a restriction imposed from outside the laws of physics. It is a structural feature that emerges from the deepest mathematical description of spacetime and quantum processes. Nothing in physics forbids faster-than-light motion in the same way that a rule forbids a particular action. Instead, the quantum structure of spacetime makes superluminal motion meaningless. There is no path within the quantum sum of possible histories that contributes to observable reality if that path involves faster-than-light motion. Such contributions cancel out through destructive interference before they can affect the physical world. In this sense, what Feynman uncovered was not a new barrier placed on motion. He showed that the speed of light limit was never really a prohibition at all. It is simply a description of how quantum amplitudes combine to produce the reality we observe. Paths that would require faster-than-light travel eliminate themselves mathematically. They cancel before leaving any trace in measurable phenomena. The universe does not forbid these paths. They simply do not contribute to reality. The mathematics that Richard Feynman developed continues to underpin every successful theory of fundamental physics. His diagrams remain standard tools used by particle physicists around the world. And his path integral formulation forms the conceptual foundation for modern research areas such as string theory, quantum gravity, and many frontiers of theoretical physics that extend far beyond what existed during his lifetime. All of this work points toward the same deep truth. The speed of light is not simply the universe's speed limit. It is the speed at which the universe updates itself. It defines the rate at which cause can produce effect and sets the fundamental rhythm of reality. Nothing travels faster because, within the quantum mechanical structure from which spacetime emerges, the idea of faster simply has no meaning. Feynman passed away in 1988 after transforming physics many times throughout his career. He contributed to the development of the atomic bomb, helped create the modern theory of quantum electrodynamics, explained the strange behavior of superfluid helium, proposed the concept of quantum computing decades before it became technologically feasible, and played an important role in understanding the weak nuclear force. Any one of these achievements would have secured a lasting reputation for a scientist. Together they established Feynman as one of the most influential physicists of the 20th century. His most profound contribution may be the realization that the speed of light limit is woven directly into the quantum foundations of reality. Embedded in the rules that govern how probability amplitudes combine to produce the physical universe we observe. What remains is understanding what this truly means. If the speed of light is really the speed of causality, rather than simply a property of electromagnetic radiation, then it tells us something profound about the nature of space, time, and the universe itself. The final piece of the puzzle reveals that this cosmic limit shapes everything from the arrow of time to the structure of the observable universe. The barrier is not merely a feature of physics. It is part of the very foundation on which physical reality is built. In fact, the speed of light has nothing specifically to do with light itself. This statement sounds paradoxical at first, but photons move at this speed simply because they are massless particles. Not because the speed belongs to them. Any massless particle must travel at exactly the same speed. If gravitons exist, they would move at this speed as well. Gluons also move at this speed. Although they remain confined within atomic nuclei, the cosmic speed limit existed long before the first photon appeared in the early universe. A more accurate description of this constant would be the speed of causality. It represents the maximum rate at which any cause can produce any effect anywhere in the universe. Every interaction, every force, and every transfer of information must respect this limit. Not because some external mechanism enforces it, but because faster causality would have no consistent meaning within the mathematical structure of spacetime. To understand this more clearly, consider what causality means in its simplest form. One event influences another. A rock strikes a window and the window shatters. The striking happens before the shattering, and the striking causes the shattering. This ordering of events seems so obvious that we rarely stop to examine it closely. Yet the entire structure of physics depends on this relationship between cause and effect. But this relationship requires something deeper. Information about the rock's motion must reach the window before the window can respond. The window cannot shatter in anticipation of a rock that has not yet arrived. Cause must come before effect. The causal connection itself must propagate through space, and it must do so at a finite speed. That speed also has an absolute upper limit. Nothing in the universe can transmit cause to effect faster than 299,792 kilometers per second. Not electromagnetic forces, not gravity, not the strong nuclear force that binds quarks into protons, and not any mechanism physicists have ever discovered or even imagined. the limit is universal and applies to every known physical phenomenon. When you push one end of a rigid rod, the other end does not move instantly. Your push creates a compression wave that travels through the material at the speed of sound within that substance. In steel, compression waves travel at roughly 5 kilometers per second. If the rod were 1 meter long, the far end would begin moving about 0.2 of a millisecond after you pushed the near end. This delay is far too small for human senses to notice. But it is completely real. Even if you could build a rod from the stiffest material imaginable, the compression wave could never travel faster than light. The speed of sound in any material must remain below the speed of light because sound waves carry information. And information cannot travel faster than causality allows. At first glance, this might seem like an engineering limitation rather than a fundamental law. Perhaps some exotic material could transmit forces more quickly. Perhaps some clever design could bypass the delay. But every attempt to imagine such mechanisms quickly collapses into logical contradiction. The speed of causality is not simply a barrier imposed on an otherwise unrestricted universe. It is a fundamental property of how reality itself is structured. It is a structural feature of reality itself. Special relativity reveals why this limit protects the logical structure of cause and effect. Albert Einstein discovered that space and time are not separate, absolute quantities, but interwoven aspects of a single spacetime fabric. Observers moving at different velocities measure different distances between events, and they measure different amounts of time separating those events. These differences are not mistakes or illusions. They are genuine consequences of how spacetime works. Events that cannot causally influence one another are separated by what physicists call a space-like interval. For such events, something remarkable happens. Different observers can disagree about which event occurred first. One observer watching events A and B might see A happen before B. Another observer moving at a different velocity might see B occur before A. A third observer could even measure them as happening at the same time. This reversal in temporal ordering can sound unsettling. How can the sequence of events depend on who is observing them? Does the universe not possess a single objective timeline? The answer is both yes and no. For events that can causally influence one another, all observers agree on the order. If event A causes event B, every observer in the universe will see A occur before B. The causal sequence remains absolute and objective. But when two events cannot influence each other at all, the universe does not define a single universal ordering between them. In those cases, the concept of which happened first depends on the observer's motion through spacetime. Neither event causes the other. Neither event influences the other. The question of which happened first has no absolute answer, because the question itself assumes a connection that simply does not exist. This is where the speed of light becomes essential. The speed of light defines the boundary between events that can be causally connected and events that cannot. If the spatial distance between two events is greater than the distance light could travel during the time separating them, those events are said to be space-like separated. In that situation, neither event can cause the other, and their temporal order depends on the observer. If the time between two events is long enough for light to travel across the distance separating them, the events are time-like separated. In this case, one event can influence the other, and every observer will agree on the order in which they occurred. There is also a third possibility. When the spatial distance between two events is exactly equal to the distance light travels during their time separation, the events are light-like separated. In this case, a beam of light leaving one event would arrive precisely at the other. These three categories form the geometric structure of causality in spacetime. Every event in the universe can be imagined as sitting at the tip of a double cone that extends into both the past and the future. The future light cone contains all events that this event could possibly influence. The past light cone contains all events that could have influenced it. Everything outside those cones lies beyond any causal connection. Those events cannot affect this one, and this event cannot affect them. Your future light cone at this moment contains every location you could possibly influence through any action you take. If you turned on a powerful laser right now, the beam would expand outward at light speed, marking the boundary of your potential influence. Anything beyond that expanding sphere cannot be affected by anything you do. Your past light cone contains everything that could possibly have contributed to your present state. Light from distant stars that entered your eyes helped shape neural activity in your brain. Cosmic rays from ancient supernovae triggered mutations in the DNA of your distant ancestors. But only events inside your past light cone could have played any role in bringing you to this moment. Everything outside that cone is causally irrelevant to your existence. The speed of light determines the shape of these cones. If light traveled faster, the cones would expand, enlarging the region of the universe that could be causally connected. If light traveled more slowly, the cones would shrink, reducing the domain of possible influence. The particular value we observe creates the specific causal structure that our universe possesses. Faster than light travel would change space-like separations into causal connections. This is not simply forbidden by a rule imposed on physics. It would create logical contradictions that cannot be resolved within any consistent framework. If you could travel faster than light, you could reach events that currently lie in the space-like region of your space-time diagram. But those events have no fixed temporal order. Some observers would see them as occurring in your future, while others would see them as happening in your past. By traveling to such events, you would convert an observer-dependent ordering into a direct causal interaction. The mathematics of special relativity shows that faster-than-light travel is effectively equivalent to traveling backward in time. Different observers would disagree about whether such a journey moved forward or backward through time. For some observers, you would arrive at your destination before you even departed from your starting point. In their frame of reference, you would already exist at the destination while the journey had not yet begun. This situation creates causal loops that destroy logical consistency. You could receive information about future events and then use that information to change them. In doing so, you might prevent the very events that originally allowed you to obtain that information. You could even watch your own departure from the perspective of someone who has already arrived. The contradictions multiply with no possible resolution. These are not philosophical puzzles open to interpretation. They are logical impossibilities that break the mathematics underlying consistent physical laws. A universe that allowed faster-than-light travel would also allow violations of causality. Effects could occur before their causes. Information could erase itself by preventing the conditions that created it in the first place. Every experiment ever performed suggests that our universe does not behave this way. Causality unfolds in an orderly progression from past to future. Causes come before effects. Information flows forward through time, never backward. The speed of light preserves this structure by preventing any causal connection between events that are space-like separated. The geometry of spacetime itself encodes this limit directly into its mathematical structure. Physicists describe spacetime relationships using a quantity known as the spacetime interval, which combines distance and time into a single invariant measure. This interval between two events can be written as s squared equals c squared multiplied by t squared minus d squared, where c is the speed of light, t is the time separation between events, and d is the spatial distance between them. This relationship is one of the key mathematical structures that preserves the causal order of the universe. This interval has a remarkable property that surprised physicists when Albert Einstein first demonstrated it. The interval is invariant. All observers, no matter how fast they are moving, calculate exactly the same interval between any two events. They may disagree about the spatial distance between those events, and they may disagree about the amount of time separating them. But they will always agree on the value of the interval. the invariance of the spacetime interval defines the geometry of our universe. It is not Euclidean geometry, where the Pythagorean theorem determines spatial distances. Instead, spacetime follows the geometry of Hermann Minkowski, often called Minkowskian geometry, where a modified version of the Pythagorean relationship applies to space and time together. In this geometry, the speed of light appears as the conversion factor linking spatial and temporal dimensions. When we say that light travels at about 300,000 kilometers per second, we are really describing a geometric property of spacetime itself. 1 second of time corresponds to roughly 300,000 kilometers of space within the unified structure of spacetime. These are the natural units of the universe. An object moving at light speed travels 1 unit of space for every unit of time. In this sense, the speed of light is not simply a velocity measured as distance divided by time. It is the fundamental conversion factor between distance and time. It acts like an exchange rate that allows physicists to translate temporal intervals into spatial distances, and spatial distances into units of time. For this reason, physicists often work in systems of units where the speed of light is defined as exactly 1. By doing this, the conversion factor disappears and the deep unity between space and time becomes more transparent. Einstein's famous relation E equals mc squared contains the same conversion factor. Mass and energy are not merely connected quantities. They are the same physical entity expressed in different units, with the speed of light acting as the bridge that converts one into the other. The speed of light squared provides the conversion between units of mass and units of energy. In everyday terms, 1 kilogram of mass contains about 90 quadrillion joules of energy. This enormous number reflects the vast conversion factor that links mass and energy in nature. The quantity c squared is approximately 9 times 10 to the 16th power in metric units. Multiplying any mass by this factor gives its equivalent energy. Nuclear reactions make direct use of this relationship. When uranium atoms fission, roughly 0.1% of their mass is converted into energy. That tiny fraction, when multiplied by the immense conversion factor of the speed of light squared, produces the tremendous power released in nuclear weapons and the controlled energy generated inside nuclear power plants. The same principle explains how the sun can shine for billions of years. Inside its core, hydrogen nuclei fuse together to form helium. In this process, a small fraction of the hydrogen's mass disappears and reappears as radiant energy. That energy is what eventually reaches Earth as sunlight. The speed of light also governs gravitational phenomena with equal authority. Albert Einstein extended his theory of relativity to include gravity, revealing that massive objects curve the fabric of spacetime around them. What we experience as gravity is actually the motion of objects through this curved geometry. When a massive body moves, the curvature of spacetime around it must change. The question then becomes, how fast can that change propagate through the universe? The answer is the same fundamental limit, the speed of light. Disturbances in the gravitational field travel through spacetime at exactly the same speed as disturbances in the electromagnetic field. The discovery of gravitational waves provided dramatic confirmation of this prediction. These waves are ripples in spacetime itself, spreading outward from violent cosmic events at precisely the universal speed of causality. When massive objects accelerate violently, they create ripples in spacetime that spread outward like waves on the surface of a pond. These disturbances, known as gravitational waves, were predicted by Albert Einstein in 1916. For nearly a century they remained purely theoretical, until 2 giant detectors of the LIGO collaboration finally observed them in 2015. The signal came from 2 merging black holes more than 1 billion light-years away. As those black holes spiraled together, they shook the fabric of space-time itself, sending gravitational waves racing across the universe. When those waves reached Earth, They stretched and compressed space by incredibly tiny amounts, changes smaller than the width of an atomic nucleus. Yet LIGO's instruments were precise enough to measure them. Because the detectors in Louisiana and Washington are separated by thousands of kilometers, scientists could compare the arrival times of the waves. The difference between those arrivals was only a few milliseconds. From this delay, physicists could calculate how fast the gravitational disturbance had traveled. The result was astonishingly precise. The speed matched the speed of light to within, better than 1 part in a million billion. In other words, gravity and electromagnetism propagate through the universe at exactly the same fundamental speed. This is not a coincidence. It reflects the deeper role of the speed of light as the universal speed of causality. All forces that are carried by massless particles must propagate at this velocity. Photons mediate the electromagnetic force. The hypothetical particles of gravity, known as gravitons, would also be massless, and therefore would move at the same speed. Any interaction carried by a massless mediator is constrained by the same limit. The universality of this speed limit reveals something profound. It is not really a property of light that happens to apply to other phenomena. Instead, it is a property of spacetime itself that every phenomenon must obey. The speed of light is therefore the rate at which spacetime can update. It is the maximum speed at which the universe can change from one physical configuration to another. From this perspective, the cosmic speed limit is not a barrier that prevents faster motion. It is a description of how the structure of reality itself operates. It is the fundamental tempo of reality, the maximum frame rate at which existence can process change. Asking why nothing moves faster than light is like asking why reality cannot update faster than it already does. The question almost answers itself. The cosmic speed limit also shapes the large-scale structure of the universe in ways most people rarely consider. The universe we observe has a boundary, not because space itself ends, but because light from beyond certain distances has not yet had time to reach us. This boundary is known as the observable universe. Today, that horizon lies about 46 billion light-years away in every direction. At first, this number sounds paradoxical. The universe is only about 13.8 billion years old. So how can the observable edge be much farther away than the age of the universe would suggest? The answer lies in cosmic expansion. Since the moment of the Big Bang, space itself has been stretching. Light that left a distant galaxy billions of years ago traveled through a universe that was continuously expanding as the light moved across it. By the time that light finally reaches Earth, the region that emitted it has been carried much farther away by the expansion of space. As a result, the galaxy that produced the light we see today may now be about 46 billion light-years away. Even though the light itself has been traveling for only 13.8 billion years. Beyond this cosmic horizon lie vast regions of the universe that we can never observe. They almost certainly contain galaxies, stars, and planets. It is even possible that some of those distant regions host intelligent civilizations, but because of the universal speed limit imposed by the structure of space-time, light from those regions will never reach us. They remain forever beyond the boundary of our observable cosmos. No information from those distant regions has reached us because the speed of light limits how fast information can travel. And the universe is simply not old enough for signals from those distances to have arrived. The situation becomes even more dramatic as cosmic expansion continues to accelerate. A mysterious component known as dark energy is pushing distant galaxies away from us faster and faster. Beyond a certain distance, galaxies appear to recede from us faster than the speed of light. This does not mean the galaxies themselves are moving through space faster than light. Instead, the space between us and those galaxies is expanding so rapidly that the total separation grows faster than light could cross it. Over immense cosmic distances, the expansion of space can exceed the speed of light without violating the principles of relativity. Many of these distant galaxies have already crossed beyond our cosmic horizon. We can still observe the ancient light they emitted billions of years ago, long before the expansion carried them so far away. But any light they emit today will never reach us. Those galaxies have become permanently disconnected from our future. Nothing that happens in those distant systems can influence us, and nothing we do could ever affect them. The universal speed limit imposed by spacetime has effectively isolated vast regions of the cosmos from one another. As expansion continues to accelerate, this isolation will grow more extreme. In roughly 100 billion years, only the galaxies gravitationally bound to our local group will remain visible in the sky. Everything else will have disappeared beyond the cosmic horizon. Future astronomers living in that far distant era might conclude that their entire universe consists only of a single galactic cluster surrounded by emptiness. They would see no evidence of the Big Bang because the faint glow of the cosmic microwave background would have stretched to wavelengths too long to detect. They would also see no evidence that the universe is expanding, because all visible galaxies in their sky would belong to the same gravitationally bound system, slowly orbiting one another. To them, the cosmos might appear static and isolated, hiding the true history of the universe that once existed beyond their horizon. The speed of light, combined with accelerating cosmic expansion, will eventually erase much of the observable evidence of cosmic history. Over immense spans of time, the signals that reveal the universe's origins will fade beyond our reach. This leads to deeper questions about entropy and the arrow of time. The second law of thermodynamics tells us that entropy, often described as a measure of disorder, increases over time in closed systems. Hot coffee gradually cools. Organized structures slowly decay. In general, physical systems evolve from more ordered states toward more disordered ones. This steady increase of entropy defines the direction of time itself. It creates the arrow that points from past to future. Yet a profound puzzle remains. Why does entropy increase toward the future rather than toward the past? Most fundamental laws of physics are time-symmetric. If the equations describing motion and interaction are run backward, they still produce valid physical descriptions. The laws themselves do not select a preferred direction of time. The explanation involves the spread of information, and here the speed of light becomes crucial. Any region that begins in a low entropy configuration tends to evolve toward higher entropy because there are vastly more high entropy states available than ordered ones. But this transformation requires information about the system's state to spread outward into the surrounding environment. As information disperses, correlations form between the system and its surroundings. This spreading of correlations increases the total entropy of the combined system. Information cannot propagate arbitrarily fast. It spreads outward at speeds up to, but never exceeding, the universal causal limit set by the speed of light. In this way, the speed of light governs how quickly information about local states can disperse through the universe. Because entropy growth depends on this dispersal of information, the cosmic speed limit indirectly determines how rapidly entropy can increase across large scales. A universe with a different causal speed limit would possess a very different thermodynamic character. If the speed of light were slower, correlations would spread more slowly, and the rise of entropy might proceed at a gentler pace. Complex structures could potentially persist longer before dissolving into disorder. A faster causal speed would accelerate thermalization across the universe, potentially preventing complex structures from forming at all. Instead, we live in a universe where the speed of causality allows stars to burn steadily for billions of years before thermodynamic equilibrium eventually claims them. It allows planets to cool, chemical systems to grow more complex, and stable environments to persist long enough for life to emerge. In this universe, biological evolution can unfold across countless generations before the distant era of cosmic heat death arrives. This balance between stability and change may not be accidental. Physicists sometimes discuss this idea through what is known as the anthropic principle. The principle suggests that observers can only exist in universes whose physical parameters allow observers to form in the first place. If the speed of light were drastically different, the formation of stars, planets, or complex chemistry might never occur. And no conscious beings would exist to ask why the universe has the properties it does. In this sense, we observe the particular value of the speed of light because it is among the values compatible with the existence of observers. However, this reasoning does not truly explain why the constant has this specific value rather than another. It only explains why it should not surprise us that we find ourselves in a universe where the value allows life. The deeper question of why the fundamental constants of nature take the values they do remains one of the greatest unsolved problems in physics. The speed of light also connects deeply with quantum mechanics through relationships that go beyond what Richard Feynman explored in his path integral formulation. Another key principle comes from Werner Heisenberg, who discovered that certain pairs of physical quantities cannot be known with unlimited precision at the same time. This idea is known as the uncertainty principle. Position and momentum form one such pair. Energy and time form another. These uncertainty relations involve Planck's constant, the fundamental quantum of action that sets the scale of quantum phenomena. When energy and momentum are related for particles moving at relativistic speeds, the speed of light appears once again as the crucial conversion factor. In the relativistic form of the uncertainty relations, light speed connects the spatial and temporal aspects of quantum uncertainty, linking the structure of spacetime with the probabilistic nature of quantum mechanics. Quantum field theory unifies quantum mechanics with the principles of special relativity. But this unification only works at one specific cosmic speed. When physicists attempt to construct quantum theories in which fields propagate faster than light, the mathematics quickly collapses into contradictions. Probabilities can become negative. Conservation laws break down, and causality begins to contradict itself. The equations simply refuse to remain coherent. The only quantum field theories that remain logically consistent are those in which the speed of light appears naturally as the maximum speed at which any field or interaction can propagate. This limit is not an extra rule added after the fact. It arises automatically when the theory is required to remain mathematically consistent. The quantum nature of matter and the relativistic structure of spacetime fit together only under this particular cosmic constraint. Some speculative ideas have suggested that the speed of light might not always have been constant. Certain cosmological models propose that light could have traveled faster in the early universe, or that its value might vary slightly across space. These so-called variable speed of light theories attempt to explain large-scale features of the cosmos without invoking cosmic inflation. However, experiments have searched for evidence of such variations with extraordinary precision. Laboratory measurements test whether the speed of light depends on direction, environment, or local physical conditions. So far, every experiment has confirmed that the speed of light remains constant to the limits of measurement accuracy. If scientists ever discovered that the speed of light truly varied, it would revolutionize physics. Fundamental constants would no longer be constant. The structure of quantum field theory would need to be rebuilt, and the foundations of cosmology would have to be reconsidered from the ground up. The consequences would ripple through every branch of modern physics. As far as current knowledge goes, the speed of light represents one of the deepest limits built into the structure of reality. It defines the ultimate boundary for how quickly information, influence, or physical change can propagate through the universe. For that reason, traveling to stars in distant galaxies within a human lifetime appears impossible for any technology that respects the known laws of physics. The nearest major galaxy, Andromeda Galaxy, lies about 2 million light-years away. Even if a spacecraft could travel at 99% of the speed of light, the journey would still require roughly 2.5 million years of Earth time. Relativistic time dilation would shorten the experience for the travelers themselves. From their perspective, the trip might feel far shorter. But if they ever returned, they would arrive to a world millions of years older. Everyone they once knew would be gone. Human civilization would likely be completely transformed, or perhaps no longer exist at all. Interstellar travel within our own galaxy faces similar constraints. Though on a smaller scale, the nearest star system, Alpha Centauri, lies about 4.4 light-years away. A spacecraft traveling at 10% of the speed of light, far beyond any propulsion system currently imaginable, would still require about 44 years just to arrive. Even at that scale, the effects of time would reshape the lives of those left behind. Travelers returning home would find their friends older, their children grown, and the world they once knew changed. Communication across cosmic distances faces the same fundamental limit. A message sent to a civilization in another galaxy would require millions of years to arrive, and a reply would take millions more. Meaningful conversation with intelligent beings in distant galaxies becomes impossible even in principle. The speed of light separates cosmic civilizations as effectively as walls of impenetrable matter. This isolation also applies to distant regions of our own observable universe. If we sent a message today to a galaxy 10 billion light-years away, the signal might never reach its destination. The expansion of the universe would carry that galaxy away faster than light could cross the growing distance between us. In this way, the speed of light does not merely limit motion, it defines the boundaries of communication, influence, and connection across the cosmos. We may be cosmically isolated not because the universe lacks other civilizations, but because the structure of the universe makes communication across immense distances effectively impossible. The same limit that separates distant worlds also protects the coherence of reality itself. Without the universal speed limit set by the speed of light, causality would collapse into paradox. Effects could occur before their causes. Information might travel backward through time. The orderly sequence of events from which meaning and structure arise would dissolve into logical contradiction. Even our ability to think depends on this causal order. Signals must travel through the brain in a definite sequence. Sensory inputs act as causes, producing perceptions and responses as effects. Memories record events that happened in the past, not events that have not yet occurred. Consciousness itself relies on the temporal structure that the speed of light ultimately enforces. A universe without a cosmic speed limit would be a universe without reliable causality. Random events in the distant future could influence the past. Information about choices that have not yet been made could shape the decisions that eventually create them. In such a universe, logical consistency would break down and existence itself would become incoherent. Richard Feynman understood this connection deeply. His path integral formulation of quantum mechanics revealed that contributions corresponding to faster-than-light motion cancel themselves out in the mathematics of quantum theory. The famous Feynman diagrams that physicists use to calculate particle interactions also encode causal structure directly into the equations of particle physics. In this way, his entire approach to physics reinforced the idea that the speed of light is not merely a property of light itself, but the fundamental tempo at which reality unfolds. The barrier is not a wall preventing passage. It is a structural feature of how existence itself works. There is no hidden side to break through, because faster-than-light motion is not a coherent concept within the mathematical framework that describes reality. Asking how to exceed the speed of light is like asking how to find a point north of the North Pole. The question assumes the existence of something that simply is not there. You are reading these words in a universe governed by fundamental constraints that we did not choose and cannot alter. The speed of light defines the boundary of causality. It shapes the geometry of spacetime, the behavior of quantum fields, and the ultimate limits of how far influence or information can travel. Nothing we build can bypass these limits, and nothing we discover can remove them. They are woven into the fabric of existence itself, deeper than matter, deeper than energy, and even deeper than space and time as we experience them. The speed of light is not a restriction imposed on reality from the outside. It is one of the properties that makes reality possible at all. It is the tempo at which the universe updates, the frame rate of the cosmos, the fundamental rhythm underlying everything from tiny quantum fluctuations to the collisions of entire galaxies. Richard Feynman spent much of his career revealing how this rhythm emerges from the deepest principles of physics. His path integral formulation showed that contributions corresponding to faster-than-light motion vanish from quantum calculations before they can affect observable outcomes. His famous diagrams encoded causal structure directly into the mathematics of particle interactions. Through this framework, it became clear that the cosmic speed limit was never an arbitrary rule added to physics. It arises naturally from the way quantum fields and relativistic spacetime fit together. The universe does not forbid faster-than-light travel in the way a law forbids an action. It simply never allows such motion to become part of physical reality. The universe is constructed from components for which faster-than-light motion has no meaning. There is nothing to forbid, because there is nothing there to forbid. We live inside a cosmos defined by boundaries that shape every event that has ever happened. Your past light cone contains everything that could have influenced your existence. Every star that shone on Earth, every supernova that scattered the elements in your body, every signal that ever reached this moment. Your future light cone contains everything you could ever influence in return. Every action, every thought, every signal that spreads outward from you into the universe. And beyond those cones lies the vast majority of space-time regions forever disconnected from us. Places we will never see and never reach. But this is not a tragedy. It is the price of a universe that makes sense. Without the cosmic speed limit, causality would collapse into paradox. Effects could precede causes. Information could travel backward through time. Reality itself would dissolve into contradiction. Instead, the universe runs on a single rhythm. The speed of light is the tempo of that rhythm, the universal metronome that governs everything from quantum fluctuations to the motion of galaxies. Every photon, every gravitational ripple, every interaction in every atom moves to this same cosmic beat. The universe cannot run faster than this, because this rhythm is not something the universe follows. It is what the universe is. The boundary that limits us is also the structure that makes existence possible. And tonight, as the Earth turns quietly beneath the stars, that same cosmic rhythm continues carrying galaxies through space, carrying light across billions of years, and carrying us gently forward through time. So relax, let the universe keep its steady tempo, and sleep well beneath the stars.